What if adding a single control qubit to your quantum simulation multiplied your entire circuit depth by a staggering factor of 18? This massive overhead is the main barrier keeping powerful algorithms like phase estimation out of reach for today's hardware. The core problem is that promoting a standard time evolution operator to a controlled operation incurs a prohibitive cost, often increasing circuit depth by 15 to 18 times. This bottleneck effectively blocks us from running quantum phase estimation on current noisy intermediate-scale quantum devices, or NISQ. This creates a dilemma because classical methods like Monte Carlo fail on frustrated systems due to the sign problem. While quantum phase estimation offers a provable advantage for these exact scenarios, it has historically required circuit depths that result in too much noise. To solve this, the researchers introduce a method called Translationally Invariant Compressed Control, or TICC, which fundamentally changes how we construct these circuits. The authors propose splitting the variational parameters into two groups: uncontrolled red layers that scale with time, and controlled green layers that remain fixed. This architectural shift converts the control overhead from a multiplicative factor into a manageable additive constant. Rather than controlling every single gate individually, the method optimizes the gates to approximate forward evolution when the control bit is 1, and backward evolution when it is 0. This clever use of control equivalence allows the bulk of the circuit to remain uncontrolled and efficient. The researchers structure these circuits using a brickwall ansatz that respects the physics of information propagation. As shown here, the design leverages the finite velocity of information flow to keep interactions local and efficient. A key advantage of this locality is transferability. The authors can optimize gates on a tiny system of just 4 to 6 qubits. Because of the Lieb-Robinson bound, these same gates can then be tiled to simulate much larger lattices without retraining. To prove this works, they implemented the method on a 36-qubit system using the Quantinuum H2 emulator. They achieved sub-1% ground state energy error using only 414 2-qubit gates, a remarkably low count for a frustrated system. However, this efficiency relies heavily on system symmetry. The method is restricted to translationally invariant, local Hamiltonians. Additionally, the maximum evolution time is bounded by the system size to maintain the validity of the approximation. Despite these limits, the work effectively moves quantum phase estimation from theory into the currently executable regime. It allows us to tackle the sign problem on available NISQ hardware today, rather than waiting for fully fault-tolerant machines. The authors demonstrate that by compressing control overhead, we can unlock quantum advantage for frustrated systems today. To learn more, head to emergentmind.com.